Alrighty, kiddos. Welcome back on this beautiful Thanksgiving Eve afternoon. I doubt you're watching it on Thanksgiving Eve, but that's when I'm recording, so hope you're having a good break. Today we're going to tackle the second to last section in Chapter 3, 3.9, so-called Additional Applications of Absolute Extrema. So we're kind of switching gears from what our focus has been on 3.3 to 3.7, which is using the first and second derivative to figure out characteristics of the graph of a function. And we're going to be returning to some application-based problems where we're going to use the first and now the second derivative to key in on absolute extrema of certain functions that model real life situations. We're going to look at minimizing surface area of a tin can. We're going to look at optimizing the dimensions of a box based on how much each part of the box costs to produce. And then we'll be looking at another cylinder situation, trying to minimize the material necessary. And so all of these are going to require us to look at either a maximum or minimum on a interval, which sounds very similar to what we were doing in section 3.2. The key difference in what we're doing today, and the reason that this comes after sections 3.3 to 3.7, is that we won't technically be able to use the extreme value theorem. You might be thinking, what's the extreme value theorem? Okay, well, the extreme value theorem tells us that if you've got a closed interval and a continuous function in that closed interval, you can basically look for your critical numbers, see what function value you get there, compare them to your endpoints, and just pick out your absolute extremum. The biggest is your absolute maximum, the smallest is the absolute minimum, and you just pull them out. Okay, and keep in mind that we did that before we learned anything about the first or second derivative test. We were just using the first derivative to find those critical points and saying, let's check these points out. Wherever you got the biggest value was your absolute extremum, and wherever you got the smallest value was your absolute maximum, and the smallest was the absolute minimum. Okay, so that was an application of the extreme value theorem. But the extreme value theorem has the condition that it has to be a closed interval. There has to be that ability to check your critical points and the function values at those critical points against the endpoints on that interval. And if you don't have that, then it won't work. And so what we're going to look at in 3.9 is functions where we cannot close the domain. And we'll see why as we work through these. Something about how the function is defined makes it so that you can't close off the interval or the domain. And so we can't technically apply the extreme value theorem, but what we can do is sort of do a little loophole, a little workaround, where if we have a situation where there's only one critical number, regardless of what the endpoints are doing, if there's only one critical number, we can use the second derivative test or the first derivative test to determine whether that's a maximum or a minimum. Okay, because even if you've got an open interval, there's only one critical number, there's no way for like funny business to happen in between the intervals. Even if it shoots off towards negative infinity on both sides, and that's why we can't close it, that critical point's got to be the absolute extreme. Okay, and so the big difference that we're looking at here between 3.2 and 3.9 is we're not using extreme value theorem here because we can't check the endpoints, and we will be using either the first or second derivative test, which is something we did not do in 3.2. So this is kind of a more focused look at finding absolute extrema. So all that said, if you would open up your notebooks, I will share my document camera. am I doing here? This is not going to work. Let's slide this over. Sorry, working at the kitchen table is a little bit of an adjustment for me. There we go. That'll work. Will it work? That'll work. Sure. Okay. So 3.9 additional applications of absolute extremum. We will jot down what I kind of just informally said. The theorem that allows us to sort of circumvent the extreme value theorem. I do want to have some rigor here that, okay, this is a legal move, what we're about to do. It doesn't have a real name, we just call it 3.9.1 theorem. And what it says is that suppose the function f is continuous. We still need continuity, just like we do with the extreme value theorem. Is continuous on the interval I. I don't know why I capitalized interval, but I did. Containing the number c. If f of c is a relative extremum, of f on I, and c is the only number in I for which f has a relative extremum, then f of c, the function value at c, is an absolute extremum. Okay. And at that point, once we've verified that there's only one critical number, we'll use the second derivative test to figure out just exactly what type of absolute extremum it is. Okay, so notice there's nothing about I being closed like we had in 3.2. We don't need to close the interval. We don't need to check the endpoints. We don't need to compare it to other critical points because there will be no other critical points because the theorem dictates that it must be the only critical point. C's got to be the only one that has that relative extremum. And in that case, when it's the only one, even though we can't make a call on the endpoints because there are no endpoints, at least not defined endpoints, we can still conclude that that's an absolute extremum if we met that criteria. Okay, so let's go ahead and jump in and see what is a situation where we would need this. What does a function look like that will not have a closed domain? Okay, so to do that, we will look at example 1 from your textbook. And the situation example 1 is a manufacturer of tin cans. I think they're making tuna, or just tin. Doesn't say what they're putting in the cans. But it says, if a closed tin can of volume 60 cubic inches is to be in the form of a right circular cylinder, find analytically the base radius of the can if the least amount of tin is to be used in its manufacture. Okay, so you can picture this situation that you've got some manufacturer of a tinned good, maybe it's tuna, maybe it's soup, whatever, and they know that they need to put a certain volume inside that can. Well, you can imagine there's multiple ways to achieve a given volume depending on the dimensions of the tin can. And as a manufacturer, you want to make the one that's going to cost you the least. Okay? And so we are going to optimize what is the dimension we're looking at? The radius of the can in such a way that it's going to use the least amount of material. Okay, so minimizing the surface area given a certain volume. And we're going to see that when we do that, there is going to be a function defined in such a way that the endpoints are going to get a little wonky. Now it says that the first example pertains to the situation discussed in example 5, section 1.3. Refer back to that example at this time. Do we need to do that? No, we'll just redo it. We're dolphins. So let's draw this thing. So, well, first let's say tin can, whose volume is 60 cubic inches. And what we want, or the what the heck thing, WTH, we want minimum surface area. Okay, so let's draw this tin can, right circular cylinder. Got a height, it's got a radius. Cool. The volume we know is 60 cubic inches, but more specifically, the volume of a cylinder is the area of its base times its height. Well, the area of the base of a cylinder is a circle, so pi r squared times the height. And this, of course, equal to 60. Okay. What about the surface area, though? Let's think about that a little bit. Go back to geometry land. Our surface area, well, we've got these two bases that are circles. So the surface area there is each pi r squared. We got two of them, so two bases, plus the area of this other stuff, which I think the technical term is the lateral area, but we'll just call it the other stuff. And you remember that moment in geometry where you realized that the lateral area of a cylinder was actually a rectangle, which was kind of mind-blowing because it's like, well, it's got a circle though. Well, yeah, but you unfold that label and you get a rectangle. And so the dimension of that rectangle will be the circumference of that circle times the height. And we've got just one of those. So what do we got? Circumference is going to be 2 pi r times the height. Cool. So we want this function in terms of the radius because we are going to be finding the minimum radius, or we're going to be finding the radius that produces the minimum surface area. So right now, this is dependent upon both the radius and the height. So what do? We look to our other equation where we also have radius and height. And if we redefine this equation in terms of the height, or define the height in terms of the radius, we can then do a little switcheroo and have this surface area just in terms of the radius. So the height in terms of our radius based on the volume is going to be 60 divided by pi r squared. So now we can define the surface area as a function of the radius by making this swap. Surface area with respect to the radius is going to be 2 pi r squared plus 2 pi r, subbing in the h now is 60 over pi r squared. Those pi's will go away. This r will go away, and that square will go away. And so our surface area with respect to the radius is going to be 2 pi r squared plus 120, 2 times 60 divided by r, because only one of those r's got canceled out there. And so now we start to see the domain here gets a little weird, because remember back to 3.2, we could make these like non-existent cylinders and it kind of worked. Okay, but the surface area is going to blow up on us if we try to make the radius 0. Okay, so the domain of this guy here, and the reason that the extreme value theorem is a non-starter for us, is that the endpoints of our domain are open. Starting at 0, this is not going to be closed because you can't have a 0 radius in this function. And then really, it would be weird, but you could extend this radius as big as you want. And so this is a positive infinity. With 3.2, we had some kind of artificial constraints where it was like 0 to 300 or whatever. I don't know if you just heard my neighbor. I think she fell and tripped and now she's crying. Very sad. Cute little like 2-year-old. Anyway, so because this is an open domain, not closed, can't just do the check the critical points and then check the endpoints, find the maximum. Okay. So now we're going to find some derivatives of S of A. So the first derivative of SA, SA prime of R, is going to be the derivative with respect to R. And we're going to be looking at, I'm going to redefine this as 120 R to the negative first plus 2 pi R squared. And we're going to differentiate this with respect to R. So we'll drop down this -1, which will give us negative 120 R to the negative second. Here, power rule again gives us 4 pi R. Okay. Do we want to jump straight to the second derivative? Yeah, because the game plan here is we're going to find the critical numbers of our first derivative, well, and verify that there's only one so that we can use this theorem up here and then use the second derivative test to see what kind of extremum it is. So since we're in the computational mode, let's just go ahead and do the second derivative as well, which is the derivative with respect to R of this guy, negative 120 R to the negative second plus 4 pi R, which is going to be like positive 240 R to the negative third plus 4 pi. Cool, cool, cool. So we've got our first and second derivative. Now the question is, okay, what's going on with our possible critical points and relative extrema? So this guy might be easier to see if we rewrite this. Negative 120 over R squared plus 4 pi times R. Critical points of our derivative are where it does not exist or where it's equal to 0. Well, the obvious thing that jumps out is that this derivative will not exist when R is equal to 0 because this quotient blows up. However, 0, not in our domain, so it can't be a critical number. Okay, so that means, and everywhere else we're safe. You can plug anything else for R here and we're okay. So we want to find the critical number that's actually in our domain, which means we're going to be looking for when does this thing equal 0. Okay, so we can write that out just so it's clear that SA prime of R dne for R equal to 0. So there is kind of that tricky moment where we can't get caught up, or that we always need to check our critical numbers against the domain. Can't be a critical number if it's not in our domain. So it does not exist for R equal to 0. However, 0 is not in domain of our original function. So we're going to laser in on when is SA prime of R equal to 0. Well, it's going to be equal to 0 when negative 120 pi, or negative 120 over R squared, plus 4 pi R is equal to 0. That's the definition of SA prime of R. I'm going to go ahead and get rid of this fraction by multiplying everything through by R squared. We need negative 120 plus 4 pi R cubed to be equal to 0. We need 4 pi R cubed equal to 120. So we need R cubed to be equal to 120 divided by 4 pi, which means that we need R to be equal to the cube root of 30 over pi. 30 over pi. Okay. And because this is the only critical number, okay, that lies in that interval, there's only one. We can apply 3.9.1 to say, oh, okay, well, that's a relative extremum. And so now it must be an absolute extremum. And so the question is, what type? Is it a max or a min? And that's where this second derivative comes in. If we use the second derivative test, because we can't use extreme value theorem to check what kind of extremum we have at cube root of 30 divided by pi. So we'll see what is the value, the positivity or the negativity of our second derivative at this R value. Be equal to 240 over R cubed, where the R that we are testing is cube root of 30 pi's plus 4 pi. And here we can pretty much stop because we can hopefully see that this, oh, sorry, there's a cube here. This is going to be positive, and we're adding something positive. This is a positive second derivative. So we don't really care exactly what it is, just what its sign is. Because this positive tells us that our function is concave up at that point. Coupling that with the fact that our first derivative is 0, we've got a horizontal tangent with a graph that's concave up, that's got to be a minimum. So previously, we would just be able to say, oh, this is a relative minimum. But now it's the only one. Now we say absolute. Kind of cool. So that's the absolute minimum now, based on 3.9.1. And so wrapping this up with a conclusion, maybe you're the logistic guy or girl at this tin manufacturer company and you do this calculus and you bring it to your boss. You're like, hey boss, here's what this means. The least amount of tin to manufacture that can of certain volume, the least amount of tin to manufacture a can of volume 60 cubic inches is achieved when the radius of the can is the cube root of 30 divided by pi. And maybe that's not a very useful number for your manager, so you'd say, oh, which is approximately equal to like 2.12. Okay. So, and you could, if you were interested, you could put this value back into the surface area function and say, okay, and this is what the actual surface area is. Okay, because maybe you had a cost associated with the surface area, and you could see exactly what that cost would be. But we were just asked for the radius, so we found the radius. I'm sorry, this should be in inches. Inches, inches, inches. Okay. So just kind of recapping what we did, because this is sort of the format we'll use. Figure out what they wanted from us. We established a function of just one variable, the variable that they're sort of asking us about. We determined that the domain, because of the nature of our function, was going to be open. Okay, we could not close a domain here, which meant that the extreme value theorem was closed to us, but that we could still use the first and second derivative to find a critical point. And because it was just a single critical point and a single relative extremum, we could then make that jump to saying that it's an absolute extremum, which point the second derivative comes in to tell us what type of extremum. Okay, that, oh, because the second derivative is positive, that means our graph is concave up at this critical point, at this relative extremum, which corresponds to a relative minimum, which, because of the nature of our function, means that's actually the absolute minimum, not just a relative. Cool. Cool, cool, cool. Okay, so just kind of walking through these calmly and deliberately and using our knowledge from chapter 3 to zone in on where those extremum are. Okay. All right. So let's move on. Example 2. Like I said, we're going to do 3 examples. I think there's 4 examples in the book, but we're going to skip one of them. One of them is just like, or very similar to the one we just did, but they don't give you a volume. They just say, hey, what's like the relationship between max or minimizing surface area based on a volume? So that's kind of a cool problem, but it's very similar to the one we just did. So I'll let you guys kind of peruse that on your own. Example 2 is, the situation is a closed box with a square base, so a prism, is to have a volume of 2,000 cubic inches. So again, fixed volume. What's the catch here? The catch is that the material for the top and the bottom of the box is to cost 3 cents per square inch, and the material for the sides is to cost 1.5 cents per square inch. Estimate on a graph to calculate the dimensions of the box so that the cost of the material is least. Confirm the estimate analytically. Okay, so again, we're trying to minimize cost in this situation with a fixed volume, but parts of the box cost different things. And so we want to minimize the area of the top and bottom of our box. Okay, so example 2. We've got situation here. We've got the volume of a prism is equal to 2,000 cubic inches. And we've got that the top of the box costs 3 cents per square inch. Sides $1.50, half the cost. And we are looking for the dimensions to minimize the cost. So this is not exactly the same as the one we just did, where we were just trying to blanket statement minimize the surface area. This is what I call more of an optimization problem, where we're trying to optimize the surface area in such a way that we minimize just a part of it, okay? So it's going to follow a similar flow where we're going to have one equation based on the volume. We're going to kind of set up like a surface area and see if we can make some connection happen there where we can have the surface area somehow just based on the dimension of the top of our box or the dimensions of the top of our box, and then minimize that, okay? So let's draw a picture. I think a picture will be helpful. So we're going to do a prism. Do they specify that it's a square? Yeah, square base. That's helpful. That is real helpful. Okay, so it's not just a prism, it's a square prism. Meaning the bases are squares. Okay. Not my best work. You're gonna have to bear with it. Okay, so the square aspect of our bases is important, which means there's really only two different dimensions to this box. Usually with a prism, we have, base, width, and height. Here, the width and the length, however you want to call it, are both the same. We'll call them x, because it's a square. Okay, which means that the bases are x squared. And then the height of the box is a different dimension. That's going to change. And so each of these side panels is going to have a dimension or an area of x times y. 4 times. I'm not going to make that too confusing. Maybe I will. Why not? X times y. And x times y. 1, 2, 3, 4. Okay. So, as I said, kind of proceeding somewhat similarly to the tin can. We know that the volume is 2,000 inches cubed. And we know that the volume of this square prism is going to be x times y. Base, length, height. Okay. So 2,000 is equal to x squared times y. The thing that we are concerned with is specifically the cost. So we're going to set up a second function, second equation called C. The cost is going to be based on this 3 cents for the top. Well, the 3 cents refers to these x squared sections. And we've got 2 of those. So 2 of those bases have areas of x squared. So whatever the x squared area is, double that because there's 2 of them, and then it's 3 cents. Plus 1.5 times 4 of those side panels whose areas are each xy. Okay. So our cost then is going to be 6x squared plus 1.5 times 4 is also 6 xy. Okay, but that's not a function yet because it's dependent upon 2 things. So we need to somehow sub out one of these things. For my money, it's going to be easier to sub out the y. And so what we're going to be finding is the cost in terms of the x dimension, but then we can use that to find the y dimension. So it shouldn't be too big of a problem. So the y then that we're going to sub in for is going to be based on this volume equation. We can rearrange this to say that y in terms of x is 20,000 divided by x squared. And so now we can rewrite the cost as a function of x, specifically 6x squared plus 6x times 2,000 over x squared, subbing in this for y. Which means that our cost in terms of x, the dimension of our base, is 6x squared. The x will cancel with one of these, plus 2,000 divided by x. And so again, we run into this issue with our domain. That because our cost function is defined this way, we can't actually have 0 as our starting point, because that would blow this up. And so this is going to be an open interval starting at 0. And then we can really make that x as big as we want. So again, that'll go to positive infinity, which is again not going to be closed. So this open domain means we can't use extreme value theorem, which means we're going to be trying to rely on 3.9.1, which means hunting down our critical numbers and hoping that there's only one of them. Then using our second derivative to determine exactly what type of extremum that is, and then concluding that that's actually the absolute extremum on this open interval. So let's go ahead and do the derivatives. C prime x is going to be the derivative with respect to x of 6x squared plus 2,000 times x to the negative first, which is equal to like 12x minus 2,000 times x to the negative second. Let's go ahead and do the second derivative as well. C double prime of x is equal to the derivative with respect to x of 12x minus 2,000 times x to the negative second. So the second derivative is the derivative of the first derivative, which is equal to 12 plus 4,000 x to the negative third. Okay, and I'm going to just sort of jump the gun here, just looking at this second derivative and looking at our domain. Everything we plug in here is going to be positive. Okay, there's no place that the second derivative is going to be anything but positive. It means it's going to be a concave up graph anywhere, which means that any critical point that we find has got to be a minimum. Okay, so we will show that. We'll do the second derivative test, but kind of our flyby second derivative test says it's going to be a minimum. Okay, we've got 12 and we're adding 4,000 divided by a positive number. That's going to be a positive number. Okay, but so what we need to do is look for the critical numbers on our first derivative. We again have this potential gotcha moment. We're looking at this. We're tempted to say, because it's true, that the first derivative does not exist for x equals to 0, and calling that a critical point. However, we wrote it right above it just to like kind of make it clear. 0 is not part of our domain, so it cannot be a critical number. Even though it's true that the first derivative doesn't exist there, it's not in our domain, not a critical number. And so just as we did with example 1, we're only going to be looking for when this is equal to 0. Because everywhere else other than 0, this is going to exist. So there's no more DNE critical numbers. It's just equals 0. So we need 12x minus 2,000 over x squared equal to 0. We'll multiply through the x squared to get rid of the fraction. 12x cubed minus 2,000 equal to 0. 12x cubed is equal to 2,000. And so dividing by, did I screw up something here? Looking at my notes from last year leads me to believe that I did. Or maybe I screwed something up. Oh, yeah, you big dingus. You guys have probably been yelling at the computer, hopefully, because you're paying attention, but I can't hear you because time and space doesn't work that way. This was the incorrect function. I forgot to multiply 6 and 2,000. This should be 12,000, 12,000, 12,000, 12,000, 12,000, 12,000. That was a lot of boo-boos, but kind of an easy fix because it was just off by one little number, which means that over here in our second derivative, that's going to be a little bit harder to fix. So this would be plus 20. Oh, it still worked out kind of nice, huh? 24,000. Anyway, and our previous comment about this being positive maintains its truth, even though I made that arithmetic mistake. Okay, so now x cubed is going to be 1,000, which means that x is equal to 10. Cool. Cool. And this is the only critical number. Okay. Well, what about negative 10? Well, what about negative 10? Negative 10 cubed is not 1,000. It's negative 1,000. Dang. Even if this was a square, and like this was 100, let's say, and you're like, oh, well, it could be negative 10 or positive 10. Nah. Same issue that 0 didn't work. Negative 10 would not be part of our domain. Okay, so we're just looking for the critical numbers in our domain, and 10 is the only one. So armed with that, we know that this is a relative min. Let's find out what kind based on our second derivative. Actually, maybe let's just be like blaringly clear about this. Only critical number on domain, which is what we need in order to apply that 3.9.1 theorem. Cool. So second derivative test on 10 would be 12 plus 24,000 divided by 10 cubed, which is like 1,000. So this is like 12 plus 24, which is like 36, which is certainly positive, like we anticipated. And so we conclude that C is concave up at x equals 10, and everywhere else too, let's be clear. So therefore, C of 10 is a relative min, but because it's the only relative extremum, we get to say it's actually the absolute minimum. Okay, because basically what's happening is it's the minimum. Towards 0, it shoots up towards positive infinity, and towards positive infinity, it also shoots up towards positive infinity. So you might be thinking, well, why? Maybe you're not thinking that, but I'll just do a quick flyby. As this becomes 0, yeah, this part goes away, but think about what's happening at 2,000 divided by things that are approaching 0. It's getting really, really big. If you divide something by a super small number, it gets really big. So as we get to 0, and sorry, but I left my graphing calculator at school. This graph is going up towards positive infinity. And so too, when x gets really, really big, because while this part will kind of get eliminated, 2,000 divided by a million or 10 million is like 0. but like 10 million squared times 6 is a super big number. It's got that kind of curve thing going on. Okay, so it's not exactly a parabola, but it does have sort of that parabolic nature to it. It's concave up the whole way, and it's just got one little turning point. And it happens to be when x is 10. And then, so we were asked for the dimension. So we found one of the dimensions. So we should probably go all the way here. Remembering that x gave us this dimension of the square sides. But let's also find what the height would be, because they did ask us for the full dimensions to minimize the cost, not just the one dimension. So to do that, we can use this equation here, plugging in our value for x. Okay. So find y. We're going to use that 2,000. Our volume is equal to x squared times y. But now we know that x squared, to minimize that cost, has to be 10. So 2,000 is equal to 10 squared times y, which is like 100. And so y is going to be equal to 20. So putting this all together and convincing somebody that you actually know what this means, we'll say that for a square prism of volume 2,000 cubic inches with, we'll just say, the given cost constraints. I can actually reprint what those costs were, but with the given cost restraints. The cost of production is minimized when the sides of the base are 10 bases are 10 inches, and the height of the box is 20 inches. Okay. And again, if we had been asked or wanted to, we could find out what that actual cost is by doing C of 10, which I guess just real quick in your brain you can do. 20 divided by 10, or 2,000 divided by 10 is 200. It's going to be 200 plus 600, 800 inches. Sorry, 800 cents. So $8. It's an expensive box. Cool. Cool. Okay, last one. We're going to skip ejemplo numero 3. Yeah. Okay. And then go to example 4, which is going to be like kind of a doozy, but the dolphins. Ends up. Oh, yeah, I forgot about this one. Oh, got some trig stuff going on. Yeah, gonna be good. If you're not ready, I would say press pause, stand up, stretch out, and go for a walk, because this one's gonna blow your hair back a little bit. So here's the sitch. Call this example 4 because that's what it is. A right circular cylinder is to be inscribed, oh, that's a fancy word, in a sphere of given radius. Okay. find the ratio of the height to the base radius of the cylinder having the largest lateral surface area. So let's say that again like 7 times. Find the ratio of the height, I'm assuming of the cylinder, ratio of the height to the radius, which gives the largest lateral surface area. It's okay, it's okay, it's okay. You can do this. Even if you don't know how, you do this thing where you just kind of fake it. You just start writing stuff down, start drawing pictures, and eventually maybe something will happen. You know, it's a tried and true mathematical strategy. Fake it till you make it. It works in life as well. So let's just, so it's a cylinder inscribed in a sphere, meaning like the edges of the top of your cylinder are going to touch the sphere. And you might be thinking, well, isn't there only like one way you can do that? Well, no. You could still do like a very skinny or a very fat. It just needs to be such that like the edges are going to be touching. Okay. I guess I kind of get that. So let's draw the circle or the sphere, I guess. Oh, this is going to be fun. Okay. It's okay. We can do this. We can do this. Just steady hand, steady hand. Of course, you gave me a pen. All right. Well, we'll deal with it. Okay. We know this is like a sphere situation. Okay. 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 And then inside of this, we're going to have a cylinder. All sorts of uncomfortableness going on right now. Okay. Okay. Kind of, sort of. Cool. Okay. And then we're going to be a little bit careful here because there's going to be multiple radii. Because we've got the fixed radius of our sphere. And I think we're going to take the cue of the book, and we're going to call that radius A. And kind of the easiest one to picture is just the straight across. A is going to be the radius of sphere. Okay. Then we've also got the radius of our cylinder as well, called R. And then we've got a height of our cylinder. It's going to be H. Okay, so we're kind of faking it. We're kind of drawing stuff. But we're kind of, at least if you're me, like we're kind of struggling to say, okay, well, where can all this stuff sort of connect? I don't really see a crystal clear connection between the radius of the cylinder and really any dimension of our cylinder. And some of you might be saying, whoa, 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 what about the height? Like the height's like, I don't know why I always like take that voice when I'm trying to be like the guy saying the obvious thing. None of you guys talk like that, but whatever. But like, yeah, like what about the height? Like the height looks like twice head. Yeah, but that's just how we drew it. Like you can picture that this will get kind of short and squat, and then the height's going to be just something. Okay, so it doesn't really work. So we're going to do something here that in your mind might not have been glaringly obvious, and that's fine because this is kind of a tricky problem, but that's why we're going through it together. I'm going to swing down this obvious spherical radius that we drew in such a way that it will somehow connect to our cylinder. Okay, so just picture that this radius here, we're just sliding it down, sliding it down, sliding it down, sliding it. Oh, and if we now draw this A radius so that it kind of perfectly hits the corner of our cylinder, which is kind of a weird thing to say because cylinders don't have corners since they're rounded. But this little part of our cylinder, so all I did was kind of swing this down. That's still A in there. And now maybe we're cooking with some kind of fire. I mean, I don't know, guys. Because what we're after is the lateral area. But we need the lateral area to somehow be connected to this radius A. Kinda? Oh, wait. Check this out. Right triangle. R, A. And what is this? But half of the height of our cylinder. We're in business. Maybe you don't see it yet, but I promise you, we're in business. How are we in business? Because the lateral area that we're doing here, we're trying to maximize lateral area, sure. Maximize the lateral area, but based on that A thing. Okay. So the lateral area is the 2 pi r times the h. We've seen that before. But we want it in terms of A. Is that what's going on here? Yeah, we want it in terms of A. Anybody see maybe what we can do? Well, let's pull this guy out because I kind of got like H here and I've kind of got R here, but we need it in terms of A. So let's draw the triangle. I'm going to kind of do it like off over here, I guess. This is R, the radius of our cylinder. This is A, the radius of our sphere. And this is half H. And before we get all crazy, like, oh, Pythagoras, like that could get nasty real quick. Let's recognize that there's actually an angle in here. We're going to call theta. And as we squeeze this cylinder smaller, that angle is going to open up and get bigger. And as we squeeze it narrower, that angle is going to slide over and get smaller. Okay. And so the surface area of this cylinder in many ways is actually dependent upon this angle here. Okay, because this angle has to kind of contract or expand based on what our height is doing. So one way to think of it is the height dictates that angle, but the flip side of that is that this angle is going to dictate the height of our cylinder, and the height of our cylinder is intimately dependent or involved with our lateral area. We're going to call this theta. And then with some trickeration here, we're going to recognize the sine of theta. So that was kind of a curveball. We're actually going to do the lateral area in terms of theta. Okay, we didn't even know theta existed until a couple seconds ago, but here we are. So the sine of theta is going to be like R over A, which means that our radius is going to be A times the sine of theta. Similar trickeration with the cosine of theta is going to be 1/2 H over A, which means that H is going to be like twice A, the cosine of theta. Okay. And maybe the A's make you uncomfortable. And I misspoke earlier, maybe you caught it, maybe you weren't. A is fixed. I should have been clear about that. Nothing depends on A other than the fact that A is just the radius, okay? And so we're gonna figure out just a given A, what are the dimensions that maximize the lateral area? And so it's really dependent upon this theta. And so the fact that A's show up in these definitions of R and H is actually okay, because in practice, we would just plug in whatever that radius is. Oh, here's a sphere that's 7 centimeters for its radius. So this is just 14 times cosine of theta. This is just 7 times the sine of theta. That's totally fine. We needed to redefine the lateral area so that R and H are defined in terms of this theta. And so doing that now, we can say that our lateral area, can we do this over here somewhere? No, we'll do it right here. Lateral area is 2 pi times a sine of theta times 2a cosine of theta. A little tight, a little tight. Maybe I should have done it somewhere else. Now we're fine. Which we're going to call that like, oh yeah, and this is where it gets really weird. Yeah, we're going to do a choose your own adventure here. So here's what we're going to do. I'm going to zoom out a little bit. Oh, this is a good problem. A lot of ins, a lot of outs, a lot of what have yous. I'm going to rewrite lateral area as a function of theta. And at this point, we've done that up here. And so this is 2 pi. And I'm going to do something kind of peculiar here, where I'm going to say that this is actually a squared out here times 2 times sine theta cosine theta. Now, this is a trig identity. And I probably said it a few times about this trig identity, so maybe we should just like commit this to memory because it ends up being useful. But I also kind of, in general, say that really the trig identities that I really need you to know are the sine squared plus cosine squared equals 1, and then like the ones that are related to that. This kind of stuff is nice, but it's not necessary, which I'll prove to you because we're going to do it like the sneaky, savvy way, where if you remember this identity, we can just do it. But then we're going to do like a choose your own adventure, the don't remember the trig identity way, and see that it results in the same endpoint. Don't remember trig identities version. Side by side, choose your own adventure. Okay, so you did remember your trig identities because you're a good little calculus student, is that 2 times the sine of theta times the cosine of theta is actually the sine of 2 theta. Who knew? Somebody knew. I think Trey knew. Trey knew last time. He probably still knows unless he forgot. So the lateral area of theta is actually equal to, 2 pi, my hip just kind of popped, times a squared. This guy becomes the sine of twice theta. Okay, which means that our derivative of that lateral area, LA prime of theta, we're differentiating with respect to theta here. It's going to be 2 pi a squared. None of these things have anything to do with theta, so they're just constants. The derivative of sine is the cosine. But we got to be careful here. Sine of 2 theta is a composite function, so we got to chain rule this son of a gun, which busts out a 2. The derivative of 2 theta is 2. Which means that our derivative is 4 pi times a squared times the cosine of 2 theta. And then we would actually do this again to find the second derivative. Again, seeing nothing here that has anything to do with theta. So just focusing here. The derivative of cosine of 2 theta is going to be the opposite of the sine of 2 theta. But again, the chain rule is going to come into play here. And so this 2 will come out. And so we'll get the negative 8 pi a squared times the sine of 2 theta. So that was definitely kind of nice if we remember this identity. Differentiating was pretty easy. And actually, we're going to just take this part of our adventure all the way to the critical point. Okay. The trig functions are such that they're going to exist everywhere. So we're really just looking for, what do we do? We didn't do the domain, did we? A lot of ins, a lot of outs, a lot of what have yous. Let's talk about the domain. That'll come into play in just a second. The domain, again, this is theta. So the domain, it really can't be 0, because if it's 0, there is no cylinder. So open at 0. This angle can open up all the way to 90 degrees, but it can't actually be 90 degrees, because then again, the cylinder disappears. It's going to be 0 to pi over 2, open. So we're not going to be able to check those endpoints, meaning we're going to have not the extreme value theorem. Okay, this problem is all over the place, but we're okay. We're progressing. So we need, I'm going to skip a couple lines here. Need the first derivative equal to 0. In other words, we need 2 pi a squared, 4 pi a squared times the cosine of 2 theta equals 0. All this stuff is just constants. We don't care about that. We need the cosine of 2 theta equals 0. When is the cosine equal to 0? On our domain, it's when, I see what's happening here. Yeah, this is going to be tricky again. Oh, I love this problem. Okay, so when theta, or when the argument is equal to pi over 2. So we need 2 theta, the thing we're putting into cosine, to be pi over 2. And you might be thinking, wait, that's not part of our domain. Yeah, but check out what we're about to do. Divide by 2, theta is equal to pi over 4, which most certainly is in our domain. So that's our critical number. And we have a 45-degree angle. That's going to be one of our critical numbers. And actually, it's the only one. So that's going to maximize, as we see in a second. Okay. Now you might be thinking, okay, well, that went pretty smoothly because I remember my trig identity. What if you didn't? We have this whole right side of the page to muddle through that process, and it will be muddling, let me tell you. So if you reach this point in our process and you're like, yeah, sine of 2 or 2 sine of theta times cosine of theta, nothing, crickets. You would have done this and said that this thing is equal to 4 pi a squared, pi a, times the sine of theta, cosine of theta, which meant that in this version of events, the first derivative, we're differentiating this guy with respect to theta. It's going to be like, actually going to be kind of savvy about this. We're going to do 4 pi a, pi a times this derivative, which will be product rule, and it's kind of nasty, but we can do it. We're dolphins. Everything. Well, how come you can pull that out? Because it's a constant. Okay. Now we know that the derivative of some constant times a function is just that constant times the derivative of that function. Totally fine. Okay. So let's differentiate that. 4 pi a squared. Derivative of this guy, maybe the product rule. Do I have enough room there? I hope so. So derivative of the first thing is the cosine times the second thing is the cosine plus the first thing times the derivative of the second thing, the opposite of the sign. And so we get 4 pi a squared times cosine squared theta minus sine squared theta. That doesn't make us feel very good because that does not look the same as that. But we're going to keep trudging. When in doubt, just trudge. Finding the second derivative here. We'll do the same thing. We'll just differentiate this guy. So 4 pi a squared, derivative with respect to theta of cosine squared theta minus sine squared theta. Nope, little 2, not big 2. Yeah, we're okay. I'm moving out here, guys. It's okay. It's been a long day. 4 pi a squared. Derivative of this guy, remember that cosine squared theta is really like cosine theta squared. So that's a composite, which means that that'll turn into 2 times the cosine of theta, but then chain rule busts out a sine of theta. Again, cosine squared, and hopefully you see that. Cosine theta squared, you differentiate that, you get 2 times the cosine of theta, but then you also have to differentiate this inner thing, which busts out the sine of theta. Yay. Go back and review your trig derivatives. You don't get that. Same thing going on here. I think that might turn into a, no, it won't. 2 sine of theta, but then differentiating that inner function, we get cosine of theta. Okay, and that's actually the same, is it? I'm taking crazy pills. Turning to 0. And drugs. What's going on? Oh, what's going on is I didn't differentiate this right. This is a negative. Yeah, that shouldn't turn into a 0. That would have been weird. And then maybe we would be on drugs. Okay. So now, yeah, these are the same, but this is a negative 2 and a negative 2 makes a negative 4. We get a negative 16 pi a squared times cosine theta sine theta. Simplifying. Okay, so we still need in this alternate version of events, version 2 we'll call it, because version 1. We still need LA prime of theta equals 0, but now the first derivative is this nasty guy. So we need in version 2, 4 pi a squared times cosine squared theta minus sine squared theta equals 0. Much like over here, we don't give much of a care about that. So really we need this guy to equal 0. And we need cosine squared theta to equal sine squared theta. It really means we need the cosine to equal the sine. And that happens precisely at pi over 4. Would you look at that? Even on the same line, it's almost like I planned it. Huh. Whether we were super savvy and use the trig identity, our critical number is when theta is pi over 4. Or if we fumbled our way through this, we didn't remember this guy, we still got that our critical number was when theta was pi over 4. Whew. I love it when that works. Like the best thing ever. So now we have our one and only critical number on the domain. And so now we just need to verify whether it's a maximum or a minimum. Second derivative, we're not going to do it both ways. We're just going to do it one way because I'm ready to be done. I think you are too. So second derivative test, we're going to use this version. We need to know L double prime or LA double prime of pi over 4, which is like negative 8 pi a squared, pi a, sine of twice pi over 4. So negative 8 times pi a squared of sine of pi over 2, which is like 1. This is a negative number out here. This is like negative 8 pi a squared. That's certainly going to be negative. This is a concave down point in our graph. Which means that the lateral area at pi over 4 is relative max. But because it's met that condition of being the only critical number, it's actually the absolute max. Okay, and you're like, holy moly, that's been one heck of a problem. But we're not quite done. Because I remember all the way back to the beginning, the question they posed was, and we said it like 7 times, or I said you should say it 7 times, the ratio of the height to the base radius of the cylinder. I never kid, but it's not that bad. What we need to do is take this angle, because that angle has really not much to do with the dimensions of our cylinder, except for the fact that it does if we go back to this triangle and realize that we do have a definition of our radius and our height based on exactly that angle. And so before we do the conclusion, we need to figure out, okay, the radius when our angle is pi over 4 is a times the sine of pi over 4. And then the height is twice a times the cosine of pi over 4. Both of these are pi over, or square root 2 over 2. So let's work this out. A times square root 2 over 2. And then our height is going to be equal to 2a times the square root of 2 over 2. So they're going to cancel. So then the ratio of the height to the radius, I think is what they wanted. Yeah. Is going to be square root of 2 times a over square root of 2 times a divided by 2. That radius. Oh, look at that. Those things are going to cancel. You're going to get 1 divided by 1/2, which is really just 2. Oh, that was a lot of work for an answer of 2. Okay, we don't have room for the conclusion. I'm going to verbally say the conclusion. The lateral area of this inscribed right cylinder inside the sphere, that just pricked my brain. Did you guys have to read Sphere for English 100s? That was a good book with Michael Crichton. Yeah. Anyway, the lateral area is going to be maximized when our height is double our radius. Really? I mean, actually, that's kind of satisfying. It works out that nicely. Okay, so that is 3.9, finding absolute extremum without the extreme value theorem. It was kind of fun, kind of neat. kind of cool. We will wrap up the chapter with 3.10, which is actually one of my favorite sections in the book. We use something called Newton's method, kind of out of left field in terms of its relatability to the first 9 sections, but it's kind of cool. And yeah, so look forward to that. I'll try to get that out to you before this coming weekend, so that if you really want to kind of hunker down this weekend and get these done, you can. Anyway, if you're watching this before Thanksgiving, have a wonderful Thanksgiving. If you're watching this after Thanksgiving, I hope you've had a wonderful Thanksgiving, and we will see you again real soon. Ciao.